plus 1 is yk. So epsilon, so yk plus 1 is yk minus ytk minus epsilon k, right? So correct solution, okay, so that would be y, yk plus 1 is going to be equal to y at tk. That's exact answer. That this representation is for exact value minus epsilon k. Okay, that would be equal to yk is y at, so this should be tk plus 1. This is epsilon k plus 1, and yk is y at tk plus epsilon k, okay, minus lambda delta t y at tk. What is the minus plus here? The way I have defined is this way. The error I have defined this way. So this will be minus here. Okay. All right. Okay. So now we have ytk minus epsilon. Okay. So what I did was just substituted for this yk as ytk minus epsilon k from here. Okay. The same yk over here is ytk minus epsilon k, and yk plus 1 is ytk plus 1 minus epsilon k plus 1. All right, now I know y of tk plus 1. This I know exact result. Okay, I know exact answer to this. Okay, so this will be equal to e raised to minus lambda tk plus 1 minus epsilon k plus 1 equals to e raised to minus lambda tk minus epsilon k minus lambda delta t t to e raised to minus lambda tk epsilon k. Okay, because that's correct. So, so now I'm going to do is, basically I need, remember, never lose sight of what you want to do. You want to relate these two quantities. Right? Okay. So you want to relate these two quantities. The limit that these quantities are small. Okay. So we have to remember that. We have to imagine that errors are actually small errors. Okay. They are small numbers. So this would be a small number. Okay. All right. So let's see how we can simplify this. That would give me epsilon minus epsilon k plus 1 is minus epsilon k minus e raised to minus lambda tk. And then it's a plus minus e raised to minus lambda t. K plus 1 is tk plus delta t. So this is basically this term taken on the right hand side. This is what I get. Okay. Minus lambda t raised to t sub k plus 1 is tk plus delta t. Okay. And minus lambda delta t to minus lambda tk minus epsilon k. Okay. Now this I can write down minus epsilon sub k plus, between these two terms I can take e raised to minus lambda tk outside. It's e raised to minus lambda tk 1 minus e raised to minus lambda delta t. All right, minus rest of the terms. This will reduce above minus epsilon. Okay, what do I have in mind? So next would be you just look at this expression, okay, that will be 1 minus, we need to expand this, okay, this term, to expand that, and that would imply minus epsilon k plus 1 will equal to minus epsilon k plus e raised to minus lambda tk 1 minus e raised to minus lambda t is going to be equal to 1 minus lambda delta t plus lambda square delta t square by 2 in higher order terms. Okay, so these ones cancel out. Then I have yeah, minus lambda delta t e raised to minus lambda tk minus epsilon k. The right hand side, if you look at, now again, delta t is small. In this limit of small delta t, I'm going to ignore higher order terms in delta t. So delta t square will always be much smaller than delta t. Okay, so this term will dominate as we reduce delta t. Okay, these terms will be smaller and higher order terms will be even smaller. So I'm going to consider this only this term. Approximate that. In the limit delta t going to 0, I get minus epsilon k plus 1 is minus epsilon k. And then if I just consider only this term, okay, that is with a minus already appearing over here and a minus, that becomes plus. So lambda delta t plus lambda delta t into e raised to minus lambda tk. And minus lambda t e raised to minus lambda tk. These two terms will cancel. Okay. All right, and other terms I have already ignored. So what I'll be left with will be epsilon k is looking like minus epsilon k plus epsilon k into lambda delta t. Okay, therefore I can write this down as, I can just take negative sign out. Epsilon k plus 1 is epsilon k 1 minus lambda delta t. Okay, that's a very simple looking expression after all this calculation, right? All it's doing, all the way it's helping me is that it's giving me what is the max. So if you know epsilon k plus 1, that is error, is magnified by this factor. So this is magnification factor of the error. In each subsequent step, in one step, okay, so in one step, that would be your magnification. So if you look at n number of steps, so suppose I start from k and go to k plus 1th, k plus nth step, each step will accumulate, will basically multiply with this factor, keep on multiplying. The next step, this will be this number raised to n. Okay, 1 minus lambda delta t raised to n. Okay, now, so now what? When do we? When are we? So let me rewrite this. What I obtained is that epsilon k plus 1 is epsilon k 1 minus lambda delta t. Okay, so this is a magnification factor. Okay, and I know that my error will eventually, so what I want actually is this number, magnitude of this number to be smaller than 1. Okay, so need 1 minus lambda delta t to be smaller than 1 for stability. If it is equal to 1, it's called marginally stable, but you want this to be smaller than 1 so that at each subsequent step the error becomes smaller and smaller and smaller and eventually it goes to 0, right? So that's the meaning of stability, so that error does not blow up. Okay, so that error does not blow up. Okay, so error does not blow up, meaning this condition has to be satisfied. Okay, now what does that mean? So if this number is positive, so that would mean 1 minus lambda t delta t is less than 1. That would lead to the condition that lambda delta t is positive. Well, that's obvious. That is automatically satisfied because lambda is a positive number to begin with. Okay, so I probably did not mention that, but here in this problem, in this differential equation problem, okay, lambda is positive. Okay, that's how you get e to minus lambda t. The solution decays with time. Okay, so lambda is already positive, and delta t is a positive number, so this is automatically satisfied. But remember, it's a magnitude. So if this number is less than 1, I get an opposite. Less than 0, this thing is positive, then you all know that mod x is x when x is positive, mod x is minus x when x is negative. So that would lead to lambda delta t minus 1 should be less than equal to 1. Okay, and that would give me lambda delta t is less than 2. Okay, and that would lead to condition that delta t should be less than 2 by lambda. Okay, so this gives me, that's what I meant by saying that the stability condition would be satisfied only when the maximum value of delta t is 2 by lambda. Okay, it should be positive anyway, that's fine, but any positive number cannot be chosen. It has to have a value which is 2 by lambda, and that would be delta t is 2 by lambda, satisfied stability. This is a threshold value you have to be careful about when you implement. This was, so now this value, remember one catch point here is that I showed that this time step value or the threshold time step value is obtained for a particular problem, particular differential equation. Okay, and this was used for just for illustrating how errors can be actually, how errors can blow up. Okay, and how, what is the way of doing error analysis. Okay, this is the way of doing error analysis for any particular method that you, any numerical method where you use discrete or finite difference method, or any kind of any method based on discretizing the space. Okay, or discretizing the axis would lead to an error, and that error you can look at. This just to illustrate how you do the errors, how you relate errors at subsequent steps, right? So for this particular problem, okay, although I've shown that what only this holds only for this particular problem, according to this, you can raise a question that said this is for this particular problem. How about in general? Will this happen in general? Answer is yes. Okay, but we will not go into that detail. I just took this example to demonstrate that delta t has a threshold limit, and that applies generally. Applies generally, and what that value is for different problems, you can actually analyze it and find it out the way we did here, right? Apply generally to other problems, as well. Okay. Now let's look at the backward Euler method if applied to the same problem. Okay. Applying backward Euler. Same problem. Same problem. Okay. So, so what does the backward Euler says? Yk plus 1 equals to yk plus delta t f tk plus 1 comma yk plus 1. Okay, and the same thing, exactly the same analysis. Yk plus 1 is y at tk plus 1, tk plus 1 plus epsilon k plus 1. That is y at tk, where y with the brackets is an exact solution, y with a subscript is a computed solution, right? So this plus epsilon k, okay, plus delta t f. F now is for our particular problem. Okay, it was delta t times f. F is minus the lambda y minus lambda y k plus 1. Okay, so here now I have to take yk plus 1 instead of yk. Okay, so that would give me ytk plus 1 is e is to minus lambda ek plus 1 plus epsilon k plus 1 should it be y tk plus 1 minus e k plus 1? Okay, this is the equations. One of them is so remember which step you were talking about, where in backward or forward? Backward. So backward may y, so let's look at this. Ytk plus 1 minus, oh, okay, right, okay, the way I have defined, well, you're right, absolutely right, absolutely right. So well, yeah, it should be minus. It does not matter actually, because if you switch the sign of the definition, because I took minus every, if you take plus everywhere or minus, you're right, but according to my convention it should have been minus. So you're right. Absolutely right. So to the question now, let me correct this. K plus 1 would be minus number k plus 1 would be y of k plus 1 minus epsilon k plus 2. So that's fine. So that, so notation t k plus 1. That's fine. So y k plus 1 is like y t k plus 1 minus epsilon k plus 1, and here minus, here is minus. So basically, well, uh, so here I defined epsilon k as computed actual minus computed. If you flip the sign, you can always define it to be computed minus actual. That can also be defined as an error. So I had that in mind. That's why I wrote it. And it does not matter. If you write plus here, write plus everywhere. If you write minus here, if you write plus here, plus here, plus here, minus here, minus here, minus here. As long as you do that, just stick to the convention. And so we have a question. Just a second. What will be the lambda if divided in some other type of function? So no, yeah, right. So lambda, exactly, that's what I said. In other type of problems, you will have to actually evaluate, okay? And the lambda will depends on what kind of parameters appear in other kind of equation, what form, etc. Okay, we have to look at the functional form of f in other problems, right? Uh, so, but actually, to tell you, uh, it's a very well, how to say this? If something is unstable, if a method is unstable to a problem that predicts exponential decay, okay, then it will generally be unstable. So it's enough for us to check the stability of a problem by looking at, by applying that method to this particular problem. So this particular problem that I just stated, that's first order reaction or the radioactive decay, okay, that particular problem is of interest because if you can show that a particular method is a particular method gives me stability for this method or instability for this method, you are pretty much comfortable that other problems will also behave in the same way. Okay, that's why, that's basically the purpose of discussing this particular problem. Okay, but exact values of delta t for other problems will have to be actually do the numerical analysis and find it out. Okay? we'll not go into that level of discussion. This is not a numerical analysis course. This is more like methods and implementing it on computers and simulating it and analyzing the result and optimizing it. This is about that. This course will proceed in a different direction. Okay. So these will be like some very important ideas which are anyway relevant. That's why I'll be discussing, but not at a great length. Okay. So yeah, but your question is very valid. That is, what happens in other problems? How do you find? Well, so my answer to that is, again, I'll repeat, as long as you can ensure that a method is gives me stability, or method is stable with respect to this particular problem, it gives you certain confidence that other methods, when you apply to other methods, it will also be stable. Okay. Okay. So I hope that is fine. Then it's okay. Fine. Thank you. All right. So let's proceed now. Now I'm going to write down e raised to minus lambda tk plus 1. Okay, fine. And right hand side will be e raised to minus lambda tk minus epsilon k plus delta t and minus lambda e raised to minus lambda tk plus 1. So minus epsilon. Please correct me. Keep a tab on my relationships. Okay. Okay, fine. Delta t minus lambda. This should have been lambda multiplied by both. All right, let's proceed then. So this will be epsilon k plus 1. I should correct this again to minus here. This is minus, and this is minus 5. Okay. Epsilon k plus 1 with the minus sign is e raised to minus lambda e sub k. Let's write down minus epsilon k, and then rest of the terms, plus e raised to minus lambda t sub k. Okay. Minus e raised to minus lambda t sub k plus 1. Okay. And then this last term plus delta t, lambda outside, so it becomes lambda delta t with a minus sign. So minus lambda delta t. Okay. E raised to minus lambda t sub k plus 1. Minus epsilon sub k plus 1. Okay. Let's see. All right. Minus epsilon k plus 1 is minus epsilon k. And then between second and third terms, this one and this one, I'm going to take out e raised to minus lambda plus e raised to minus lambda dk plus 1. Okay. So that would give me e raised to minus lambda and dk minus dk plus 1. Okay. Lambda tk minus lambda tk plus 1. So okay, fine. Okay, and then minus lambda delta t e raised to minus lambda t k plus 1 minus epsilon k plus 1. Okay, all right. This quantity is what? This quantity is minus delta t. this quantity minus delta. Because delta t is a positive number between tk plus 1 minus tk. So minus delta t, so this minus plus, okay, this becomes e raised to lambda delta t minus 1, and that would give me, I expand that, I get minus epsilon k plus e raised to minus lambda t k plus 1, and I have lambda delta t, e raised to lambda delta t is 1 plus lambda delta t plus lambda delta t square by 2, and this way, and then minus 1. If 1 cancels out, and then I have minus lambda delta t e raised to minus lambda t k plus 1 plus lambda delta t epsilon equals 1. Okay, alright. Now again, delta t being small, I can ignore higher order terms. Okay, delta t square and cube and those terms are ignored because delta t is small. Okay, so leading term would be lambda delta t multiplied with e raised to minus lambda tk plus 1, and I have another term with a minus sign here, lambda delta t e raised to minus lambda tk. These two terms cancel. So I have nothing appearing from this side, and as a result, what I'm going to get is so that would give me minus epsilon k plus 1, like minus epsilon k, okay, plus lambda delta t epsilon k plus 1. Okay. All right. So that I will put like I can basically take epsilon k plus 1 on this side, and that will give me epsilon k is equal to epsilon k plus 1. Okay. 1 plus lambda delta. Correct? Yeah. Therefore, therefore, uh, that will give me epsilon k plus 1 is going to be equal to epsilon k divided by 1 plus. All right. So see the now you notice that. So apply the backward Euler to this, and this was from the backward Euler. Forward Euler gave us epsilon k plus 1 as epsilon k 1 minus lambda delta t. Okay. This is what I got from forward Euler. So here I know that lambda and delta t, they are both positive quantities. Therefore, denominator, in the case of backward Euler, denominator is always larger than 1. So 1 plus a positive number is 1, right? Therefore, epsilon k plus 1 is always going to be equal to epsilon k. And therefore, as we march along time axis, okay, error at the subsequent steps becomes smaller and smaller. Okay? And that is what leads to stability. So I hope I have probably given you sufficient. There are two ways we approached this concept of stability. One was purely geometric, looking at the curve, how we may be able to overestimate or underestimate depending on whether we are becoming more forthcoming in the forward Euler and we're becoming more conservative in the backward Euler. Okay, the slopes will be different, right? And that was geometrical interpretation and similar. And if you do the detailed mathematical analysis of errors and see and ensure and basically try to find out under what condition will the error not blow up, you arrive at this fact that backward Euler is always stable, whereas forward Euler is conditionally stable. And in this, you also gain something by this method. You also get a quantity estimate of the value of delta t. Okay, now I want to point out something here. Let's see, I'm looking at dy by, does this number which we obtained from forward Euler case, delta t less than equal to 2 by lambda. Does it make sense? Makes sense. Meaning, does it give you any feel? Why should, is it consistent with our common sense? I just want to give you that idea. So dy by dt, if I have minus lambda y, I know that y, of course, y0 is equal to 1, etc. Then y of t is e raised to minus lambda. And if you look at this, plot the curve y versus t, it's going to look like something like this. Okay, so start from 1. So start from 1 and it will look like this. Okay, well, so the plot is somewhat like this. Okay, so what is the value? What is lambda? What does lambda satisfy? Lambda actually signify. Lambda is inverse of the half half time, half lifetime, right? So lambda is a rate one, which is k inverse is proportional to actually inverse of the half life, right? So half life would be like when it takes one, or you can say that 1 by e is basically it's a measure of by certain factor an initial value will be reduced by certain factor called 1 by e, right? So so 1 by lambda you can call tau. Tau is 1 by lambda, right? So tau is 1 by lambda. So tau is a measure of half lifetime except for some constant. So now if you so this is how your dynamics occurs. Question why a variable that follows this differential equation gives me this particular dynamic behavior, right? With time is going to look like this. Now if I want to develop a method that must capture this trend, okay, that I've shown up here, I have to be, suppose I choose, so see, most of the phenomena occurs in a less than half lifetime, right? A majority of this y has decayed, nearly half of it has decayed in the time scale of 1 by lambda. Okay, okay. So if so now something is happening at that time scale and you decide to choose a time scale which is much larger than that. Okay, so suppose you decided to choose your delta t in your calculation where you're going to look at you're going to compute answers at these time temporal points, then you are going to miss major major amount of information. Okay, main information is lying in the time scale which is of this size. Okay, so that's why your delta t should be basically, and you should try to get it smaller than tau. Okay, and that's what our analysis predicts. Actually, our analysis tells me delta t is less than equal to 2 by lambda, at least 2 tau. So somewhat like delta t is less than 2 tau, you would get, as long as you are actually trying to achieve, so as long as you're trying to capture the kinetics, you have to be your time scale of the phenomena and the time scale of and the time step of your discretization should be commensurate. Okay, or at worst it should be commensurate, but you should try to make your time step at least smaller than the phenomena time scale that you're trying to capture. Okay, something is happening very fast and you are basically sampling at very slow rate, you will be missing a lot of information. Okay, so something is happening very fast and you are actually too sluggish and you decide to sample the phenomena at very large time steps, you will be missing a lot of things. You will be missing the actual phenomena. Okay, and therefore it's something is happening, so you have to be keep in pace with the phenomena, right? That's the basic idea. All right. uh okay, so that is what we obtained for, that's what we got for forward Euler. Backward Euler is always stable anyway. All right, next now um, uh, so next, so these two methods that I just discussed, they are based on finite difference approximation of derivatives. So remember, you actually uh, looked at derivatives, the finite difference expressions of the derivative, right? All right. Here, I just now let me to say a few words about the amount of error, okay? Or what we saw right now is how the error propagates, okay? That is related to the issue of stability. There is another important uh, important concern in these numerical methods, or when you implement a method, when you simulate something, is how much is the error. Okay, error is there, but is one thing how it propagates with time, and the other thing is what is the value. Okay, how much is the error, and this is basically related to the issue of accuracy of your result, how accurate you are. Okay, so there is two things: accuracy and stability. Okay, so accuracy would be, if accuracy is high, that would mean your error is small. The true value and the computed value differ by much smaller value, but by much smaller amount if the error is low and method is more accurate. Okay. So how do you quantify accuracy? Okay. How do you quantify accuracy? Well, in this case, we are going to quantify by just looking at, well, it's the same thing. Essentially, y at it's basically the value of epsilon k, or magnitude of epsilon k, is what actually tells me the accuracy. So now let's look at this. Now, uh, let's see. In general, y k plus 1. So suppose I am using forward Euler. Y k plus 1, I am going to approximate by y, sorry, this forward Euler, y k plus 1 is equal to y sub k plus delta t and f t k y, okay, where f is dy by dt. Okay, this is actually this is what you're doing. Now, actually, value of yk plus 1 would be how much? Yk plus 1, if I want to actually calculate, it's going to be equal to yk and plus delta t f tk plus delta t square by 2 f prime tk yk plus delta t cube by 3, okay, double prime tk yk, and so on, and up to all infinite terms. If I just, this is nothing but Taylor's expansion. Okay, so Taylor expansion is accurate as long as we include all the infinite terms. Okay, okay. Now, so this is my exact value. Okay, so my error is basically, what I'm doing is I'm actually ignoring this part, and this would be my error. In my calculation computed, this is my computed value, and this is my exact value. Okay, this is my exact value. And therefore, whatever terms I have basically, I have truncated this series at this point. Okay, I have truncated over here, and whatever terms I've ignored will lead to error. Okay, this will lead to error. So your error is actually, so in general, you can say that. So here, as you can see, y k plus 1, okay, is going to be equal to y of k plus 1 minus error. Okay. Just neglect all that, right? Y k plus 1 minus error. So this would give me the computed. So this is computed, and this is exact. Okay. Now this error is basically, so what we are going to look at next is error starts, in this particular case, error starts with delta t square, and goes and includes higher and higher order terms. Error, I can write this like some constant into delta t square plus some other constant into delta t cube and so on. Okay, this is my error. In the limit delta t goes to 0, okay, this would be the leading term. Okay. The leading term, the most important term, the limit delta t going to 0 is the first term. Okay. Okay. So when delta t is small. Okay. So this would constitute the main part of the error will be the first term that you have ignored. Okay. The first term that we have ignored, first term that we have ignored will be the dominant error. Other will be much smaller values, right? Okay, so now answer me this. If I have a method where I get error scaling, error going like delta t square, the dominant term like this one has dominant term error scaling as delta t square, and other method, so suppose method 1 as method 1 has error scaling as delta t square. The dominant term that we ignored is delta t square versus a method 2 where error scales as delta t cube and so on. Which one? So in general, you will get a method where errors may scale differently with respect to delta t. It may have a different exponent. Some method may be delta t4, some may be delta t square, etc. Which one do you prefer? Question is, which one do you prefer? Can anyone answer me? Yeah, absolutely right. Because, yeah, I wanted to be more accurate. Absolutely, that's correct. Because as delta t becomes small, error will be even smaller here as compared to over here, right? So we all know that. So therefore, our goal when we just develop, when we actually select a method, my accuracy is an issue, of course, meaning this error is an issue, but an additional issue that is, so error, error going to delta t raised to n, and n higher is preferred. Okay. Okay, so you always try to develop a method which is uh, which is which actually when I reduce the time step, it converges faster. Okay? That's all it means. Okay, so all right, so n higher is preferred. Now another thing here in these initial value problems, what I calculated so when I write this y, let me write down this for the forward Euler, yk plus 1 is yk plus whatever that is, delta t of dk yk, okay, and then plus error, where error I'm going to call it delta c1 and delta t square, and rest of the terms will be there, okay? So they're small. Okay? This is my error term. Okay, but remember this is the error in one step. So if I have to suppose I have to calculate it, suppose I start a calculation from zero, and I'm looking at some time t. I am actually computing my values. Okay, so I'm computing my values. Let's say I'm computing my values at some particular time t. Okay. Now the question is, what is the error that will be observed here? Okay. If this is divided into n steps, let's say this is delta t. Okay, this is delta t. Okay. Okay, so this is delta t. Then what's going to happen is each subsequent steps we are going to add. So errors in each subsequent steps will be added. So if you this is called error in one step that we have given here. This is scales as delta t square. Okay, this is called local error. Okay, and After certain steps, if I have to calculate, that will be called global error. So error accumulated after n steps. That I'm going to call global error. Actually interested in calculating the value at certain time. Okay, so how does that error look like? So errors accumulate, meaning if you sum the errors at individual steps. Okay, what I'm going to get is some C1 delta T square. Okay, and I will have n such terms, right? So each term will have some kind of error like this, and you'll have n such terms in n steps. So I'll have total error like this, and n is given by t by delta t, right? So this would be equal to e by delta t, c1 delta t square. So that it cancels out, and I get some other constant. T is a constant anyway, c2 delta t. Okay, so if you look at a global error with respect to the step size, by reduce the step size, if your local error is second order, global or error will be first order. Okay, so global error is always, local error is basically always one order higher. So global error is one order less as compared to local error. Okay, all right. So all right. So, all right. Well, actually, it's a good time to stop. Yeah. Okay. So I guess we have talked. We have so what we have done so far today. We talked about stability, and we looked at the details of how errors may propagate with reference to a particular problem, but it is generalizable in general. Okay. And then we looked at accuracies, how to quantify a method based on its accuracy. You always try to, you always want to get a method which is where the error scales with a much larger exponent as compared to much larger exponent in delta t. Okay, so when you say second order method, correct, second order correct method, that would mean the global error is delta t square, and if it's fourth order correct, then that would mean that delta t raised to 4. So that's how second order Ranga Karta, or when you get to here, this is second order, fourth order, or higher order terms, higher order methods. That would mean that you're looking at more and more accurate methods. Error is very small, and in addition, it actually quickly converges to correct answer as you reduce the delta t. Okay? So these are the things we have discussed. We look at. So now we look at these things. Uh, I want you to do these kind of numerical experiments. Now you know how to do math lab, so do these experiments. Okay, calculate error. Take up a problem. A very simple problem is, of course, the one that we just discussed. Take up a problem for which you know exact answer, and then solve it by either forward Euler or backward Euler. Okay, look at the error, look at the stability, and see how solution blows up. Those are the things that you should be able to doing. You should be doing yourselves. Okay. All right. So I'll stop here, and this is the question. I can say bye bye. Okay, then we'll stop and see tomorrow.